This is Chapter 9, Solutions, and the last section is 9.6, Properties of Solutions. We saw at the beginning of the chapter that the definition of a true solution is that it's a homogeneous mixture of the solute and solvent particles. So they're uniformly dispersed throughout one another, and you can't see or distinguish between the different parts, the different components in the solution. But there are other types of mixtures that are very similar to solutions, but that are less homogeneous, and so we can discuss them in many of the same ways. So they have a lot of the same properties, they affect the properties of the solvent the same way, and we can measure them in terms of concentration and things like that. So this distinction is really based on the size, generally speaking, of the particles that are in solution. Okay, so individual atoms or molecules will dissolve as a homogeneous, transparent solution, a true solution. Larger particles, maybe they're not totally soluble and they don't break down to the molecular level, but they come in small groups of molecules that are stuck together. Those may be considered colloids, okay? And those will start to become heterogeneous. If the particles are big enough, they'll scatter light, and so the solution will look milky or cloudy. Particles that are even larger than that can be temporarily suspended in solution or suspended in the solvent, and over time they'll settle out. Okay, those would be called suspensions. So these three different sort of types of solutions have similar properties, and so we can discuss them in many of the same ways. So in this video, we're going to talk about the distinctions between those three types and also some of the things that they have in common in as much as they change the properties of the solvent that they're dissolved in. So again, the defining characteristics of a solution are first that it's transparent, okay, so you can see through it even if it has a color. That the particles do not separate out over time. So the solute particles remain dispersed and uniformly dispersed in the solvent no matter how long you let the solution sit. And finally, these previous two are actually both consequences of the solute particles being very, very small. Okay, so we're talking about individual ions or molecules dispersed in the solvent that can't be filtered through regular filter paper or even with a semi-permeable membrane. Okay, so they'll just pass right through the holes in a filter and through the holes in a semi-permeable membrane. Okay, so solutions have the smallest solute particles, and that's what gives them these properties. Colloids have slightly larger particles, you could say medium-sized particles in general. And so these particles are large enough that they begin to scatter light in a way that makes the solution look cloudy or milky. Okay, so it still will sometimes appear homogeneous. So for instance, milk is often considered a homogeneous solution, but in one sense it's heterogeneous because the particles, the fat globules and things that make up the suspended particles in milk will scatter light, and that's why milk has a cloudy, opaque quality to it. So it's pretty stable over time, right? Milk is, or at least homogenized milk is. So colloids are still largely homogeneous depending on how you define that, but they can be cloudy or milky. They'll still not separate over time, so they'll stay well dispersed, even if you let them sit, but the particles can be now separated with a semi-permeable membrane. Okay, they'll go through regular filter paper, like a coffee filter or a laboratory filter, but a semi-permeable membrane, which is a special kind of sort of polymer membrane, will separate them out. It will trap colloid particles. Here you can just see some examples of colloids. We've already seen many examples of a true solution, but for colloids, these are some interesting examples, right? Fog and clouds and even dust and smoke are considered colloids. Your blood is considered a colloid because you have red blood cells and things suspended in your blood plasma. So those can be filtered out through proper semi-permeable membranes and things like that. Styrofoam and marshmallows are gases that are dispersed throughout a solid medium. Okay, so these are just different types of examples of colloids. The next type of mixture is called a suspension. Okay, and in a suspension, you have relatively large particles. They are large enough that the whole solution looks, again, cloudy or milky and is clearly heterogeneous. Okay, so you may see that it's non-uniform. You'll notice that the suspended particles don't disperse very well, and they'll tend to settle out of solution. So if you let it sit over time, you'll see the particles build up at the bottom as sort of a sludge or a solid at the bottom, and the liquid above it will become less concentrated as the particles come out. Okay? And so the particles in a suspension are so large that they can be filtered even with regular filter paper, sometimes even with cotton swab. You can filter out the large suspended particles. And so in order to have a suspension behave more like a solution, you have to constantly stir it. You have to keep it stirring or moving in order for the particles to stay suspended, to stay dispersed throughout the solvent. Okay, so muddy water is an example of this, calamine lotion, things like that. These are suspensions. So anything that will settle out and separate if you let it sit over time is considered a suspension. This chart just summarizes some of those properties, so you can review this if you're studying. Now we can use these properties to separate a mixture that might have a few different types of solute particles in it. You might have some small solution particles represented by these yellow circles, some medium-sized colloids represented by these bluish-green triangles, or you might have also large suspended particles represented by these red squares. So if all of these types are mixed together in one mixture, then there's a few things we can do to separate them. The first we can do is the simplest. We just wait. And over time, the suspended particles will settle to the bottom, and then we can just pour out the liquid that has the solution and the colloid particles. The next thing we can do is to use a filter, some sort of just regular filter paper. The filter paper will let the solution and colloid particles pass through, okay, but it'll trap behind the red squares, the suspended particles. And so that's one way that we could filter out the suspended particles and be left with just solution and colloid particles. And then the last thing we can do is similar, but instead of filtering it, we're going to let it go through a semi-permeable membrane. Okay, so you can collect your entire mixture in this bag, which is made of a semi-permeable membrane, and then put it into a solution or a beaker of solvent or some sort of container of solvent, and the solution particles, the small yellow circles, are the only ones that are going to pass through the surface of the bag to get into the outer solvent. Okay, so you'll trap your colloids and your suspended particles inside the bag, and you'll be able to separate the solution particles out of it. Okay, and then you can just take the bag out and you'll have a true solution left over, and your colloids and suspended particles will still be in the semi-permeable membrane bag. So a mixture that has solute particles that do not settle out but are too large to pass through a semi-permeable membrane is called a blank. Okay? So particles that do not settle out means it's not a suspension. Suspended particles will settle out. But if the particles are too large to pass through semi-permeable membrane, that means it's not a solution. Okay? So that means it must be a colloid, B. So if we have some type of mixture, whether it's a solution or a colloid or a suspension, what's going to happen is that the presence of the particles in the mixture is going to change the properties of the solvent. So for instance, we're typically talking about aqueous water solutions in this class. So when we add a solute to water, the physical properties of the water changes. The vapor pressure, the boiling point, and the freezing point are all going to change. Okay? It'll also change the density and things like that. But these particular properties are what we call colligative properties. Okay? The properties of a solution then don't depend on what type of particles you have in solution. They only depend on the concentration. Okay? So the only thing that matters for how much the boiling point is raised, for instance, is how much solute you have dissolved in the water. Okay? It doesn't matter what type of solute, only how much of it. So the first couple of properties are related, the vapor pressure and the boiling point. Okay? Increasing the concentration of solute particles in a solution decreases the number of solvent particles that are at the surface. Okay? And it's these particles at the surface that can escape into the vapor and cause the vapor pressure to accumulate. Okay? So if we reduce the amount of solvent particles at the surface, then fewer particles are going to be able to go into the vapor phase, and so you're going to lower the vapor pressure. Okay? Right? This prevents some solvent particles from leaving the solution because you have fewer particles at the surface. Since you're lowering the vapor pressure, that means that you're going to have to heat the solution higher. You're going to have to give it more energy in order to get the vapor pressure high enough to balance or overcome the atmospheric pressure. Okay, so if the vapor pressure is lowered for a given temperature, then you have to increase the temperature more to get the vapor pressure to reach atmospheric pressure, which is the definition of the boiling point. Okay, so a lower vapor pressure leads to an increased boiling point and elevates the boiling point of the solvent. So pure water boils at 100 degrees Celsius. But if you add salt or sugar or any other kind of solute to it, then it's going to boil at a higher temperature. On the other hand, the freezing point of a solution will be lowered when you add solute particles to it. Okay, so this is why they salt roads in the winter. If you add salt to an icy road, then it's going to help promote the thawing of the ice, and then once the ice has thawed, it lowers the freezing point so that it doesn't refreeze back. Okay, so this allows the ice to melt and be cleared away. Okay. Adding ethylene glycol to water increases the number of hydrogen bonds that form in the solution and lowers the freezing point and raises the boiling point of the solution. Okay, so this is antifreeze. Ethylene glycol is a form of antifreeze that you can put in your car. And so this is why you put it in, because it lowers the freezing point. Since the colligative properties depend on the number of particles dissolved in solution, we have to understand what types of solute particles we're putting in, because if you have an electrolyte versus a non-electrolyte, the particles will dissolve differently and they'll create different numbers. Okay, so in the simplest case, you have a non-electrolyte. Okay, so for example, ethylene glycol we saw as antifreeze. But when you put ethylene glycol and you mix it into water, it just goes from the liquid state to the aqueous state. It doesn't break apart, it doesn't form ions. Okay, it just changes its phase from being liquid on its own to being dispersed or dissolved or hydrated in solution. So that means that every mole of ethylene glycol that you put in just becomes 1 mole of particles in solution. Okay, it's very simple. For a solute like sodium chloride, however, which is a strong electrolyte, this is going to break down and form multiple ions. Okay, so 1 mole of sodium chloride doesn't dissolve as 1 mole of particles. It dissolves as 1 mole of sodium ions plus 1 mole of chloride ions. So from the 1 mole of sodium chloride you ended up with 2 moles of particles in solution. Okay, and so that means that it's going to effectively have double the power per mole to raise the boiling point and lower the freezing point. This table shows the effect of the number of solute particles on the boiling and freezing points. Okay, and again, it only depends on the number of solute particles dissolved. So for pure water, we have a freezing point of 0 and a boiling point of 100 degrees Celsius. Okay, we know that. If you add a mole of a non-electrolyte, then you're going to get a mole of particles dissolved, and so the freezing point will lower by 1.86 degrees Celsius. It'll go down to negative 1.86. And the boiling point will be raised to 100.51 degrees Celsius, so it goes up by 0.51. For sodium chloride, however, if you put a mole of that in, you actually get 2 moles of solute particles, and so the freezing point is lowered twice as much. So 1.86 times 2 is 3.72, and then you subtract that from the initial freezing point, which is 0, and so you get negative 3.72 degrees Celsius. For the boiling point, it raised it 0.51 degrees for 1 mole, so it will raise it twice as much, or 1.01 degrees for 2 moles. So the new boiling point will be 101.02 degrees. For calcium chloride, this is also a strong electrolyte, but it actually produces 3 moles. You get 1 calcium ion and 2 chloride ions. So you end up with a 3 times lower freezing point and a 3 times higher boiling point. In the northeastern United States, during freezing temperatures, as I said, calcium chloride is a salt that's added to icy highways to melt the ice. Okay? So what's the freezing point of a solution containing 0.50 moles of calcium chloride in 1 kilogram water? So those numbers that you saw in the previous chart are all based on adding that amount to 1 kilogram of water. So if we put a half a mole in of calcium chloride, how many solute particles are we going to get, and how much is that going to lower the freezing point? Okay. So we know we have 0.50 moles of calcium chloride in 1 kilogram of water. We want to know the new freezing point of the solution. And so we're going to need to know that the freezing point lowers 1.86 degrees for every 1 mole that you dissolve into 1 kilogram of water. So the first thing we have to do is determine the number of moles of solute by figuring out how calcium chloride breaks down. So again, it's important to know that calcium chloride forms 1 calcium ion and 2 chloride ions. So 1 mole of calcium chloride actually produces 3 moles of solute particles. So if we have a half mole of calcium chloride multiplied by 3 moles of solute per every 1 mole of calcium chloride, that's going to tell us that we have 1.5 moles of solute particles. And then we can multiply that by the factor that the freezing point is lowered by, 1.86 degrees Celsius per 1 mole of solute. Okay, so this is going to give us a change in temperature of 2.8 degrees Celsius. Okay, but remember, this is the change in temperature. So this number has to be subtracted from 0. So to get the new freezing point temperature of the solution, you take the freezing point of the water and you subtract the delta T that we just calculated. So the freezing point of water is 0 minus 2.8 gives you negative 2.8 degrees Celsius freezing point. Osmosis is another property of solutions. So in osmosis, you have water flowing from a region of lower solute concentration to a region of higher solute concentration. Okay? So imagine you have a beaker that's divided in half with this semi-permeable membrane, which does not allow particles through. Okay? So the only thing that can go through here are the water molecules. And on the left side, you have pure water, but on the right side, you have a sucrose solution. Okay? You've got some sugar molecules dissolved. The sugar molecules can't go back and forth. Okay? If the membrane were removed, then the sugar particles would just disperse evenly throughout the whole solution so that the two halves would come to the same concentration. But the barrier, the membrane, is preventing that from happening. So the only thing that can get through the membrane is a water molecule. And so what's going to happen in order for this, for these two solutions to sort of try and come to equilibrium, the water is going to go from the left-hand side, which has lower concentration, to the right-hand side, which has a higher concentration of solute. Okay? And so the water side, the pure water side, is going to drop, the level will get lower, and the side that has the higher concentration will rise, it'll get higher. Okay? And so in doing this, the left side is trying to increase its concentration, although here there's no solute, so it can't really do that. But the right-hand side is trying to decrease its concentration. Okay, so this is an effort to make these two sides come to the same concentration. So over time, the two sides will become more equal. Now in this case, they'll never be quite equal because you don't have any solute on the left-hand side, so there'll be nothing that you can do on the right-hand side to balance that. But there'll be some pressure, some flow, or some tendency for water to flow from the left side to the right side. And eventually the higher level on the right side will balance that out by causing enough gravitational pressure to fight back against that, and it'll come to equilibrium. So we can quantify osmosis through this idea of osmotic pressure. Okay? So the osmotic pressure is the pressure that will prevent the flow of additional water into the more concentrated solution. So again, in the last example, we had the right-hand side was gaining water because that's where the higher concentration was. But eventually, enough pressure was applied to the right-hand side in the form of it forming a higher, going up to a higher level, that it counteracted the flow of water through it. Okay, so at that point, it balanced the osmotic pressure. Okay, so the osmotic pressure is greater when you have more dissolved particles. Okay, so as the number of dissolved particles increases and you go to a higher concentration, you're going to have a higher osmotic pressure. In other words, a higher concentration solution is going to have more of a tendency to accept water through it or for water to flow into it. And so you're going to have to apply a greater pressure to it to prevent that water from coming through. Okay. We can also reverse this. There's a process called reverse osmosis where we apply more pressure to the high concentration side. So we apply a pressure greater than the osmotic pressure to the solution, and that forces the water back through the membrane in the reverse direction that it would naturally flow, and it causes it to purify, essentially, right? It leaves behind all those solute particles on the other side, and so you get pure water out from the other membrane, okay? But this is a very energy-intensive process. It requires a lot of energy to provide this pressure to force the water back through the filter. This concept of osmosis is very important when you're talking about biology. Okay? If you have, for instance, a red blood cell dissolved in some blood plasma, if they had very different concentrations of solute particles, salts or sugars or whatever, inside the cell versus outside the cell, then there would be a net flow of water either in or out, and that would disrupt the functioning of the cell. It might cause it to burst or to shrivel up. So it's very important for your body to regulate the concentrations in these different regions. Okay. So an isotonic solution is defined as a kind of solution that has roughly the same concentration of solute particles as you find inside your cells. Okay. This allows you to place cells into an isotonic solution without disrupting them too much, without them either swelling up or shrinking. Okay. And so this can be defined in terms of either glucose or salt. So a 5% glucose solution or a 0.9% salt solution will be isotonic with respect to most of your cells in your body. Okay. So as IV solutions in hospitals, for instance, have to be isotonic, or else when they add them to you or add them to your body, they'll cause disruptions in your cellular functioning. So we can look at this again, thinking about the example of red blood cells in your blood plasma. So for an isotonic solution, it has the same concentration of solute particles as are inside the red blood cell. So you can put a red blood cell into an isotonic solution and they'll retain their natural shape. Okay, they're circular, they have sort of a dimple in the middle of them. This is the way that a red blood cell is normally shaped. In a hypotonic solution, hypo means less than. So what this means is you have less solute particles in the solution than are found inside the red blood cell. That means that water is going to try and flow from the solution into the red blood cell to sort of equalize the concentration. Right? Once this water begins to flow into the cell, you can experience what is called hemolysis. Okay? Water flows into the cell, it causes it to swell. You can see the dimple is reduced or eliminated in a lot of these, and eventually the blood cell can actually burst. Okay, so that's called hemolysis. On the other hand, you can have a hypertonic solution. Hyper means more than, and so this has a higher concentration of solute particles that are inside the red blood cell, and so water from inside the red blood cell is going to go out of it, and it's going to cause the red blood cell to shrink. It's going to shrivel up and shrink because it loses water volume from inside. This process is called crenation. Okay, so you can see here clearly these red blood cells have shriveled and shrank a lot, and so they're no longer going to function properly. Okay, so you need an isotonic solution in order to have the red blood cells preserved. Again, a hypotonic solution has a lower solute concentration than red blood cells, so water flows into the cell by osmosis, and they can undergo hemolysis. A hypertonic solution has a higher solute concentration than red blood cells, and so water will flow out of the red blood cell, and it'll cause it to shrivel up and shrink in a process called crenation. Artificial dialysis also works partially on this same principle of osmosis. So dialysis is when you have a problem with your kidney functioning. Normally your kidneys remove excess waste and things like that from your bloodstream, but if they're not working properly, then you can undergo artificial dialysis, where your blood is taken from your body, it's run through a machine that cleans it, and then it's put back into your body. Okay, so the basic way that most people understand is that the blood comes out and it's filtered to allow the blood cells and things like that through, but keep the toxins and the more harmful metabolic waste behind. And so it filters it out that way and it puts the fresh blood back in. But it also can be used when you have too much water in your system. Okay, so the kidneys actually also regulate the water content, which helps to regulate the concentration of particles and ions and things in your body. So when you have too much water, you can also undergo this dialysis, and the water will be removed through osmosis. Okay, additional sugar and things like that are added to the dialysis liquid, and so when the blood is run through it, the water will come out of your blood and into the dialysis fluid due to that osmotic pressure. And so then the blood with the normalized amount of water will be put back into your body. Okay, so this is all based on diffusion through semi-permeable membranes and osmosis. Let's look at a few different examples. So when placed in each of the following, indicate if a red blood cell will A, not change, B, undergo hemolysis, or C, undergo crenation. So basically they want us to look at these different solution concentrations and tell whether this solution is isotonic, hypotonic, or hypertonic. Okay, so if it's isotonic, there'll be no change. If it's hypotonic, then there's less concentration than inside the red blood cell, and so the red blood cell may undergo hemolysis. If it's hypertonic, then it has a higher concentration, and so it may undergo crenation. Okay, so a 5% glucose solution is actually an isotonic solution. Okay, so A would be the answer. There would be no change in the red blood cell. A 1% glucose solution, however, is a lower percentage, right? So this is going to be hypotonic. Okay, that means it has less glucose in it than an isotonic solution, right? We saw isotonic is 5%. 1% is less than that. So what's going to happen is that water is going to flow from the solution into the red blood cell to try and equalize the concentrations. And so it's going to undergo hemolysis. Okay. For number 3, it's also a hypotonic. So 0.5% sodium chloride is less than the 0.9% threshold. So this is hypotonic for salt. And so this will also undergo hemolysis. But for sodium chloride, the threshold, the isotonic threshold, is 0.9%. So 2% is above that. So this is hypertonic. And since it's hypertonic, water is going to flow out of the red blood cell into the surrounding solution, and the red blood cell may undergo crenation. You don't actually have to memorize those thresholds for this class, so you don't necessarily have to be able to answer questions like this, but if you can understand it and go through it and see why these answers are the way they are, then you'll be in a good position to understand the concepts underlying hemolysis and crenation. Those are things that you may be tested on. That brings us to the end of Chapter 9 on solutions. And so here we see again a chart, a concept map of all the different topics that we've covered. So over here on the left-hand side, you have more of the concepts of what makes a solution, what different types of solute particles are, solubility, and things like that. Here in the middle, you have more concentration units, and these are things that you would use for calculations involving solutions. And then here you have the colligative properties and things like that, which are also an important part of solutions. So for this chapter, you should know all of these. You may be tested on any of this. As far as the relevance of this chapter to the rest of the textbook and the rest of the course, molarity is probably one of the single most important properties or concepts that you can take from this chapter. So you should know molarity, and you should know very quickly how to transform between the volume of a certain molarity solution and the number of moles of solute that represents. Okay, so take a look at that slide on how to use molarity when we're dealing with solution reactions. Okay, you use molarity to convert from volume of a solution to moles, and then mole to mole factors, and then so on from there. Okay, so this is one of the more important topics. Okay, but all of these may be tested.